In this video, I will talk about Widlar current source, how to find the output resistance of Widlar current source, Cascode current source, transistor sizing of Cascode current source, finding R out of Cascode current source, and the voltage swing of Cascode current source. Widlar current source consists of a current mirror well, but a resistor R is placed at the source of T2. So here the gate to source voltage of T1 is fixed and it is decided by Iref current. So the gate of T2 is fixed, whereas source of T2 depends on current I out flowing through resistor R. If current I out increases, then the source of T2 increases, and hence if the source voltage of T2 increases, the gate to source voltage will reduce, because gate to source voltage is gate voltage minus source voltage. So when I out increases, gate to source voltage of T2 decreases. But the gate to source voltage for Iref equals to 1 amp be equal to 0.4 volts. So for 0.4 volts of gate to source voltage, which equals to drain to source voltage, we get a current of 1 microamps. Here we have a 1:1 current mirror, that is W by L of 1 equals to W by L of 2. So we expect Iref equals to I out when the VDS voltages are same. However, the VDS of T2 is at 0.6 volts, which results in a current of 1.4 microamps for same VGS equals to 0.4 volts. So here we see I out current to be 0.4 microamps higher than Iref. To overcome this issue, a resistor is placed at the source of T2. So when the current has increased to 1.4 microamps, the voltage across the resistor has also increased. So the source voltage has increased. So since source voltage has increased, the gate to source voltage of T2 decreases. The gate to source voltage of T2 will reduce to 0.37 volts, and hence we have a new green line for VGS equals to 0.37 volts, and the corresponding current will be equal to 1 microamps. So by using a resistor, it acts like a negative feedback and it increases the output resistance. Hence, the transfer characteristics looks more or less flat when we increase the output resistance. This is called as a current sink and not as current mirror, because VGS1 is not equal to VGS2. Let us see what is the value of R out by doing a small signal analysis. So for small signal analysis, we need to short the DC voltage sources and open the DC current sources. If we consider this part of the circuit, the constant current source can be opened and the gate to source voltage can be shorted, since gate to source voltage is a constant. So when we short, gate to source is shorted, gate to drain is shorted, drain to source is shorted, so this circuit can be neglected. Now let's consider this part of the circuit. Here the gate voltage, gate to source of 1 is constant, so the gate voltage of T2 is constant, so short gate to ground and everything else remains same. So here I have the small signal model of transistor T2. Gate is grounded, source is S2, VGS equals to VG minus Vs. Vg is 0, so 0 minus Vs. Vs is nothing but Iout times R. And we have GM2 times VGS2. We have RDS2. To find R out, we have to find V out by I out. So using KVL, the voltage V out equals to current through RDS2 times RDS2, that is voltage across RDS2 plus voltage across resistor R. So V out is given by current flowing through RDS2, that is I out minus GM2 VGS2 times RDS2 plus voltage across the resistor, which is given by Vx. We know that VGS2 is nothing but minus Vs2 since Vg is grounded. So VGS2 equals to minus I out times R. Replacing minus I out times R as VGS2 by VGS2 and Vx as I out times R, we get this equation. Solving this equation, we get R out equals to RDS2 plus R plus GM2 RDS2 R. Here RDS2 plus R is small compared to GM2 RDS2 to R. So R out equals to GM2 RDS2 times R. In a Widlar current source, R out is a large value given by GM2 RDS2 times R. That is nothing but R times gain of the transistor T2, that is GM2 times RDS2. With high R out, the effect of channel length modulation is reduced. Next is Cascode Current Source. Consider the Widlar Current Source. Replace R by a constant current source, that is an NMOS whose gate to source voltage is fixed. This can be obtained by using a NMOS diode on the left branch and connecting its gate to the gate of an NMOS on the right branch, which results in a cascode current source or a sink. So here we have replaced the resistor R by an NMOS whose gate is connected to an NMOS diode, that is T4. The R out of the cascode current sink is nothing but RDS3 times gain of T2, that is GM2 RDS2. Let us derive R out of cascode current sink or a source. Consider the right branch of the cascode current sink. The gates of T2 and T3 are constant voltage, hence it is represented by VB2 and VB3. For small signal analysis, all the DC voltage sources has to be shorted to ground. So VB2 is shorted to ground and VB3 is shorted to ground. And let this node, that is the drain of T3 or the source of T2, be equal to Vx. Now let us draw the small signal model of this circuit. So we have gate of T2 which is connected to ground, source of S2, source of T2, that is S2, which equals to Vx voltage. Then we have drain of T2, which is nothing but V out. We have Gm2 times VGS2, and then we have an RDS2. And then to the source of T2 or to the drain of T3, we have a RDS3 which is connected to ground. Here Gm3 VGS3 is not present because VGS3 equals to 0. Since VB3 is, since the gate is shorted to ground and since the source is shorted to ground. Using KVL, we can say that the voltage V out equals to the current into RDS2, that is I times RDS2, that is the voltage drop across RDS2 plus the voltage drop across RDS3. So V out equals to I times RDS2 plus I out times RDS3. Current through RDS2 is small I equals to I out minus Gm2 VGS2. Therefore I equals to I out minus Gm2 VGS2. What is VGS2? It is nothing but gate of 2 minus V source of 2. Gate is grounded, so it is 0. So VGS2 equals to 0 minus VS2, which equals to minus Vx, that is voltage across the source, which equals to I out times RDS3. So VGS2 equals to minus I out times RDS3. So we can write I equals to I out, which if we take it as common, I out into 1 plus Gm2 RDS3. Therefore V out, replace I in this equation. So we get V out equals to I out into 1 plus Gm2 RDS3 into RDS2 plus I out into RDS3. Take I out common and move it to the left hand side. We get R out, that is V out by I out, equals to 1 plus Gm2 RDS3 into RDS2 plus RDS3. So we get R out equals to RDS2 plus RDS3 plus Gm2 RDS3 RDS2. Since RDS2 plus RDS3 is a small value, it's very small compared to Gm2 RDS3 RDS2, we can approximate and say that R out equals to Gm2 RDS2 times RDS3, that is this value. Therefore R out of a cascode current source or sink is nothing but RDS3 times gain of T2, that is Gm2 RDS2. So here we have increased R out and hence the effect of channel length modulation is reduced. Transistor sizing for cascode current sink. How do we size the transistors? Here we know that VGS4 equals to VGS3 because gates are shorted, source is grounded, so VGS4 equals to VGS3. We want VGS1 to be equal to VGS2. So we want VGS1 equal to VGS2. Since the gates are common, the gates gets cancelled, so minus VS1 should be equal to minus VS2, which implies VS1 should be equal to VS2. Here I've considered VS1 as Vx and Vs2 as Vy, which implies Vx should be equal to Vy. Vx is nothing but drain to source of 4 and Vy is nothing but drain to source of 3. So VDS4 should be equal to VDS3. Now take the currents, that is IRF, which is flowing through T1 and T4. Take the equation, that is the drain current equation. IRF equals to beta naught by 2 into W by L of 1 into VGS1 minus VTH the whole square equals to the current flowing through T4, that is beta naught by 2 W by L of 4 into VGS4 minus VTH the whole square. Now take the current I out, which is flowing to T2 and T3. So I out equals to beta naught by 2 into W by L of 2 into VGS2 minus VTH the whole square. Here I have written VGS2 to be equal to VGS1 because we have proved here. This current will be equal to the current through T3, which is nothing but beta naught by 2 into W by L of 3 into VGS4 minus VTH the whole square. Here VGS3 is nothing but equal to VGS4, so I have considered VGS4 here. Now divide the equations. So we get IRF by I out equals to W by L of 1 divided by W by L of 2, which equals to W by L of 4 divided by W by L of 3. This is how we size the transistors for a cascode current sink. Next, I will talk about voltage swing of normal current mirror and cascode current source. Consider the circuit of the current mirror. This is the circuit. Here, what is the voltage swing? V out minimum value cannot be equal to 0. Reason is we want the transistor T2 to be in saturation for this current mirror to work. So for T2 to be in saturation, we want the drain to source of T2, that is VDS2, to be greater than VGS2 minus VTH. So here VDS2 minimum is nothing but VGS2 minus VTH. VDS2 minimum is nothing but V out minimum. So V out minimum is nothing but VGS2 minus VTH. Here VGS2 minus VTH can be written as VGS2 effective. So V out minimum in this case is equal to VGS2 effective. Consider the cascode current source. Here V out minimum cannot be equal to 0 or ground. The reason is we want the transistor T2 and transistor T3 to be in saturation region for the cascode current sink or source to work. So here T2 should be in saturation and T3 to be in saturation. For T2 to be in saturation, we want the drain to source of 2 to be greater than VGS2 minus VTH. Can write it as greater than equal to. So VDS2 minimum is nothing but VGS2 minus VTH, which can be written as VGS2 effective. Now for T3 to be in saturation, we want VDS3 to be greater than or equal to VGS3 minus VTH. However, here we consider that Vx to be equal to Vy, which means VDS4 equals to VDS3. But VDS4 is nothing but VGS4, since the gate and the drain is shorted. So VGS4 equals to VDS3. VGS4 is nothing but VGS3. So VGS4 equals to VGS3 equals to VDS3. So here the VDS3 of T3 is a fixed value and it is fixed to VGS3, which equals to VGS4. So VDS3 equals to VGS3. We can write VGS3 as VGS3 minus VTH plus VTH, which equals to VGS3 effective plus VTH. So VDS3 is a fixed value. Its minimum value or maximum value or the average is fixed to VGS3 effective plus VTH. So V out minimum, that is this voltage minimum, will be equal to VDS2 minimum plus VDS3 minimum. So we know that VDS2 minimum equals to VGS2 effective and VDS3 minimum equals to VGS3 effective plus VTH. So V out minimum is VGS2 effective plus VGS3 effective plus VTH.